Hello everyone, we are Team ALU64 and today we are presenting our final challenge project, a PID controller for a DC motor using ROS2 and an SP32. The goal of this project was to regulate the angular velocity of a DC motor in real time using an SP32, encoder feedback, an L298N driver, and ROS2 running on an external computer. Our strategy followed a practical engineering workflow. First, we characterize the motor in open loop to identify dead zones and actual limitations. Then we convert encoder pulses into angular velocity in radians per second. Finally, we implement a PID controller from scratch and improve it with digital filtering, anti-wind-up, and live tuning. Our design was supported by both academic and practical references. The literature shows that PID remains one of the most common solutions for motor speed regulation because of its simplicity and effectiveness. It also shows that encoder-based velocity estimation requires filtering due to quantization noise, and that anti-wind-up is necessary when actual saturation is present. Our review includes 5 academic references, 2 patents, and 1 industrial development, allowing us to connect our implementation to real engineering practice. The system is organized as a 3-node ROS2 architecture under the namespace motor. The input node runs on the computer and generates the reference signal. The serial bridge also runs on the computer and connects ROS2 to the SP32 through serial communication. The control node runs on the SP32, where the real-time control loop is executed. This structure makes the system modular, scalable, and easy to launch from a single launch file with YAML-based initial parameters. This diagram shows the actual implementation flow. The input node publishes the set point. The serial bridge forwards the set point and controller gains to the SP32, and the control node computes the control action and drives the motor. Encoder feedback is read through hover interrupts, and telemetry is sent back through serial, converted into a custom ROS2 message, and visualized using plug juggler. The embedded control node runs at 50 Hz, so the sampling time is 20 milliseconds. The encoder interrupt is connected on GPO19, and the pulse per revolution value was measured experimentally as 370. Encoder counts are converted into angular velocity in radians per second, then passed through a 16-sample moving average filter before entering the controller. The final control signal is normalized in the range from -1 to 1, where the sign determines direction and the magnitude determines PWM duty cycle. The serial bridge is responsible for serial parsing, publishing the custom motor status message, and sending live tuning updates for KP, KI, and KD. The input node is responsible for reference generation and supports step, sign, and score signals. This allows us to evaluate the controller under different operating conditions without modifying the embedded implementation. The PID controller was implemented entirely from scratch. A key design decision was computing the derivative term on the measured value instead of directly on the error in order to reduce derivative keep during abrupt setpoint changes. We also include anti-wind-up to prevent excessive interval accumulation during saturation. The final gains obtained experimentally were Kp equals to 2.1, Ki equals to 3.0, and KD equals to 0.25. These values were refined through live tuning while observing the response in plug juggler. All validation in this project was performed experimentally on the real system rather than through a separate simulation model. In the square wave test, the controller tracks abrupt change in the reference while the filtering signal remains significantly smoother than the raw encoder velocity. This confirmed the importance of filtering and shows stable controller behavior during sharp transitions. In the sinusoidal test, the motor output follows the reference with relatively small tracking error and the expected phase lag of a real physical system. The comparison between raw and filtered velocity again shows the effect of the moving average filter in reducing measurement noise. In the step test, the controller maintains the motor velocity around the desired value with small oscillatory error. Based on experimental plots, the system achieves stable real-time regulation and acceptable tracking performance for all tested reference signals. In conclusion, this project achieved stable real-time speed controller of a DC motor using ROS2 and an SP32. Filtering and anti-wind-up were key to improving practical performance, while ROS2 enabled modularity, telemetry, and live tuning. Our conclusions are based on experimental validation on the real system. As future improvements, we will replace the L298N with a more efficient driver and use a stronger power source. The main risks are encoder noise, saturation, serial communication loss, and power limitations. Thank you very much.